No, it says it on screen.
Let's do the integral of 3. Wait, did we do this one already? We have not. 3 times 3x minus 1, take u to the 4th dx. And just for the sake of practice, let's use U-Substitution. Let's use U-Substitution. So the way this works is you let U equal an inside function. Do we see an inside function in there? 3x minus 1. Okay, so we're going to let U equal 3x minus 1. Okay. What is du equal to? So in this case, du is equal to 3 dx. D is a derivative, so the derivative of 3x minus 1 is just 3, right? And then you multiply the dx to the other side. So what we're trying to substitute, you guys, what we're trying to cover is the dx. We need to be able to substitute the dx. And we need to be able to substitute the 3x minus 1. Okay. So what is dx equal to? Du over 3. Okay. What do you suggest we do now? So this we replace with u. What about this 3 here?
That just stays.
What do we have a 3 and a dx we could replace with something? Isn't 3 dx equal to du? Okay. The 3 and the dx is equal to du, so we could just write this as u to the 4th times du. Because this 3x minus 1 was equal to u, and this 3x, or this 3 dx, that's just equal to du right here. So all we have is u to the 4th times du.
Oh, it's just 12 u to the 3rd.
What's the integral of u to the 4th? It's u to the 5th over 5 plus c, right? The constant here. And then you unsubstitute. Plus c.
That's your answer.
And I'm hoping that most of you can get to a point where you can visually inspect this and just do a quick derivative. If you did a quick derivative of this in your head, wouldn't the 5 drop down?
Yeah.
Cancel with that 5. This becomes 4, but then you'd have to do a chain rule, so you'd have to multiply it by 3. So the derivative of this would be 3 times 3x minus 1 to the 4th. Is that what we have here?
Basically.
So I'm hoping to get to the point where you can do just a quick derivative check. You understand what I'm saying?
Yeah, we used to do it.
Let's try part C.
Still not sure.
Integral 3x squared times the square root of x to the 3rd minus 2 dx. So what are we going to let u equal? Remember, all we want to let u equal is an inside function. Do we have an inside function?
Yeah.
There's an inside function right there. Yeah, x to the 3rd minus 2. So then du What's du? 3x squared dx. Now we've got to make sure everything is covered. This right here that I've circled, what are we going to let that equal?
U.
And then 3x squared dx. That's just du, right?
That's insane.
Is everything covered? Is there anything that's not accounted for?
No, but I'm pretty
So
sure
we can make the substitutions now. We can call this the integral of the square root of u du.
Beautiful.
Now integrals and radicals don't mix too nicely. Let's call it u to the 1/2 du. So you add 1, so it's u to the 3/2 times 2/3 plus c, and then you unsubstitute. Plus c. And again, a quick mental derivative. This is just good derivative practice. If you drop down the 3/2, wouldn't it cancel with the 2/3? And then you decrease 3/2 by 1, so it becomes 1/2, which is just a square root, isn't it? But then you have a chain rule. So we 3x squared. So we're good, right? So this is just a matter of seeing a lot of these and doing a lot of practice. Let's do part D.
All right.
No, is this C? This is part C.
That's part C. That's part C.
What is part D?
Just did part B.
Yeah.
We're gonna have an awesome party. Let's go to the party.
Let's do the integral
Party.
of cosine squared of x times sine of x dx.
Square signs. Party.
Right. Let's go to the party or be a square. We're integrating in our party.
Hold on. There's a question here we need to talk about. Go ahead. Which other formula? Oh, like the integral of a chain rule. You talking about this? Is that what you're talking about? That's what we're going to end up doing with U-substitution anyway, is we're kind of getting around doing this. Sharon! Alright, shut the files!
Last time I did.
Okay, we still are going to do a U-substitution, you guys, and I think that's going to be the easiest way to do this. So what we got to try to find is an inside function. Is there some function that's having another function happening to it?
Yeah, X.
You understand what I'm saying?
Yeah.
Like cosine x is a function, right?
Yeah.
But isn't there another function acting on it? So the cosine is an inside function, and the squared would be an outer function. You following?
Yeah.
So when you're letting u equal something, you always want to choose an inner function. So what if we let u equal cosine x?
I think that would be alright.
Would that be all right?
Yeah.
I think I'd be okay with that.
I guess that's fine.
So what's du?
Sine x cosine x.
Be careful. What's the derivative of cosine?
Negative sine.
Negative sine x dx. So I'm going to ask you to look real carefully. Is everything accounted for?
All no.
No,
It needs to be a negative sign.
Well, the square is just going to be u squared, and that's fine, because we can integrate u squared.
yeah, we don't like the negative sign.
So, is this right? Let me ask you this. Is this right here equal to du?
Oh no.
Shouldn't it be a negative sign here?
Yeah.
Now, you can't just start adding things on there. You're going to change everything. Do you remember how we took care of this, though?
Oh, we multiply it outside by negative 1. That's enough.
So if I put a negative 1 right here multiplying, didn't I have to...
Yeah.
Oh, yeah.
Put a -1 out there to multiply. You guys following?
Yeah.
Like a leader.
Now technically, if I multiplied by something here, really I should divide by it. But what's 1 divided by -1?
-1.
Still -1, so I'm just going to put in, you guys okay with that?
Yeah.
But technically you should remember, if you multiply by something here, you got to divide by it out here. We did this last time, I think. Okay. Why did this have to have a minus sign though?
So it can equal negative sine x dx.
So it could equal du, yeah. Now is everything accounted for?
Yeah.
So let's make the substitutions. What is cosine?
U
So this
squared
becomes negative integral of u squared times
du.
du.
Now we integrate.
Okay, negative. What's the antiderivative of u squared?
U cubed over 3.
U cubed over
So it's
3.
negative U cubed over 3.
And then we have this plus c over here. And then we unsubstitute, I guess you could say. Is that even a word?
Yeah.
Anti-substitute? I don't know.
D-substitute.
D-substitute. There we go. Yeah, D-substitute.
That's what we did when you were locked in the locker room that one day.
We do substitute.
We got substitute.
We got substitute.
Dang it, we did get some.
Hybrid, it's okay.
But when he came
It's
back,
a cool mistake.
hey,
Okay, are we feeling more comfortable with U-substitution?
I feel like you guys fixed the mistake.
Okay, the most important guidelines you guys to remember is how do you choose what to let U equal? Some inside function. And then when you find du, you got to make sure that this whole expression is accounted for. If you're missing pieces, you can put them in the integram, but you got to change what's outside of the integram. You follow? Okay. For the next 10 minutes, we're going to do the exact same thing, but now we're going to have bounds of integration. So these are definite integrals. You understand the difference?
Yeah.
Okay.
There just won't be a C.
There won't be a C. So let's do some definite. Definite integrals. There's a little definition I want you to write. If the function u is equal to gx as a continuous derivative and f is continuous, this first part isn't super important, it's just what the book says, and continuous on the range of G. Here's the important part. I'll give you a second to catch up. Give you a second here to catch up. Again, that first part isn't super important. But that integral I've written there, that's...
Did we already do this?
I'm gonna, there's one more part to it.
Oh, it's like...
What is this, you guys? This right here. Isn't it an application of the chain rule?
Yeah.
Right, Braden?
Yes.
There's a chain rule right here. So what we've been doing the last 15 minutes is making substitutions. Instead of f of g of x times g prime of x, didn't we just call that f of u times du?
Yeah.
Yeah. But now we change the bounds of integration. If we're going to make a substitution for u, we also have to change the bounds of integration. So instead of a, it becomes g of a. And instead of b, it becomes g of b.
Whoa.
Okay? Let me just make sure we're clear on what happened, you guys. The last 15 minutes, didn't we take something that looks like this and just change it to f of u? The only difference is we didn't have bounds of integration. Okay, now we're just going to have to change the bounds of integration. It's pretty easy. So here's an example. We're going to evaluate from 0 to 1 the integral of x times x squared plus 1 to the third dx. So we just start like normal. We let u equal something. We do a little substituting. So what are we going to let u equal?
X squared plus 1.
X squared plus 1. So then du
2x.
is 2x
dx.
dx. Now, is there anything missing?
You gotta multiply by 2. And then you gotta divide the outside by 2.
Close. We have the x dx right here, x dx. We're missing the 2. So if I put a 2 right here, that's fine. But you got to multiply out here by 1/2. You following?
Yes, sir.
So now this is 1/2 times the integral. Now I'm going to leave the bounds blank for a second because we're going to have to change these bounds. But it's going to become u to the third du. Now, our bounds of integration originally were 0 and 1. Okay? We're going to have to use this function
That's our g function.
to change the bounds of integration. Exactly, because this is our g function. U is equal to g of x. And right here I have u equal to x squared plus 1. So this is like our g of x function, according to our definition, right?
That's weird that if they ask for this circuit where you can just change their interval. Excuse me. Yeah, I don't like the interval you gave me. I'm going to change it.
So when x equals 0, what does g of 0 equal? And when x, what was the other bound of integration? 0 and 0. So when x equals 1, what's g of 1? You guys understand what I'm asking? And what's the g function?
X squared plus 1.
G is x squared plus 1, and now we have two particular x values to use. So if x is 0, that just becomes 0 squared plus 1, which is
1.
1.
Then we have 1 squared plus 1, which is 2.
And then we have 1 squared plus 1, which is 2. So those are our new bounds of integration from 1 to 2.
And then we got to use our fundamental theory of calculus.
Okay. So what's the antiderivative of u to the third?
U to the 4th over 4.
U to the 4th over 4, and that's multiplied by
1/2.
1/2, and then we have to evaluate that from
1 to 2.
1 to 2.
When you resubstitute right now?
If we're going to keep these bounds, you guys, and this is the nice thing about changing the bounds. Are you listening? If we're going to keep these changed bounds, then just keep it in terms of u.
Okay.
Because what are these bounds in terms of?
U.
They're in terms of u, so we can just keep it in terms of u right now.
What if I want in terms of V?
I was about to do
You got it.
So,
Something clever is that.
what's the antiderivative evaluated at 2? Antiderivative evaluated at 2. 2 to the 4th. 2 to the 4th is
64? 16?
16 divided by 4.
4.
So that's 4. And then we subtract the antiderivative evaluated
1/4.
at 1. This is 1 to the 4th, which is 1 divided by 4. So it's 4 minus 1/4.
Which just gives you 16 fours. So 15 fours, so 1/2 of 15 fours.
So we have 1/2 times 15 fourths,
15 eighths.
which is 15 eighths.
And you can simplify that.
So
1.5.
when you change the bounds of integration according to u, you can just leave your antiderivative in terms of u. You don't have to resubstitute. You guys following?
Will you get the same answer?
Well, that's what I was just going to show you.
Radical.
If we go back to here, 1/2 times u to the 4th over 4. If we go back and unsubstitute our substitution, what would that equal? What was u? X squared plus 1 to the 4th over 4, and then we could go back to the original bounds. Okay, would it give us the same thing? Well, because now we're in terms of x again. So we go back to the original bounds. Okay, would it give us the same thing? Well, let's see. 1 squared
1
plus 1,
2
2 to the 4th,
16
16 over 4.
4
So we have 1/2 4 there, and then minus the antiderivative is 0. 0 squared,
0
0 plus 1,
1
1 to the 4th,
1
divided by 4.
That's the exact.
gives you 15/8
So we still get 15/8.
or 1.875.
Okay, so just before the bell rings, why did we bother changing the bounds? Did it make a difference? We got the same answer.
It made it simpler.
That way we didn't change it out.
So the only reason to change bounds is if your antiderivative is super complicated. If you resubstitute, if you leave it in terms of u and change the bounds, sometimes it's easier to evaluate the antiderivative. You guys following?
Yeah, Mr. Oh.
It would be the same thing whether you do or don't change the bounds, but sometimes it's easier to change the bounds.
Goonies never say that.
All right?
I'm down when you do what he says. If you don't do what he says, you have no problems.
Right.
I feel like math, by the way, I feel like